I would like to introduce Jean-Paul Ballard. I think he's first of all an engineer with a huge passion towards aerodynamics and this like incredible combination of things which I think brings a lot of interesting angle to those problems to solve, and he's has a lot of experience with Formula One. I think over 14 years, right? And last 6, 7 running his own company, focused on aerodynamics and wheel bikes and all the things around. So give a warm round of applause to Jean-Paul and welcome. Looking forward to the talk.
Cool. Thank you, everyone. Well, I'll switch the presentation on and we can get started with the presentation. So thanks again for coming and those following on the live stream. Welcome to Free Speed. Basically a presentation over the true revolution in cycling that's happening right now. There's a massive era of revolution that's going on. And, you know, me and my team and our brand are very much sort of fueling that fire. So I thought today I'd present to you all a little bit about the technology behind this revolution and really just try and lay out some facts about aerodynamics and cycling and most importantly, how you can make yourself faster, because that's what it's all about, or more efficient. So start off with just a really simple fact. And that fact is that aerodynamic drag is the biggest resistance in cycling, and that's where most of your energy goes when you push in the pedals. That's why it is really so important. And if we look at just some basic facts again, this is measured at 35 kilometers an hour, so it's a reasonably quick speed, but almost 70% of the aerodynamic drag of the power consumed in the pedals is aerodynamic drag. Funnily enough, we've been brainwashed over the last 20 years about how important weight is, quite simply because it was the only thing we could really measure. But actually weight's relatively unimportant in the grand scheme of things. And in this case, this is actually measured over a 1,500 height meter course over 100 kilometers. Weight only contributes to 16% of the power you're putting into your pedals. The rest is rolling resistance and drivetrain losses, but as a quick taster, basically from the first screenshot we can see aerodynamic drag is very important. So as a quick intro, I'll tell you a little bit about myself and about Swisside and what we're doing in the cycling industry. Basically, we're a spin-off from Formula One motorsport, and so what we're doing is we're transferring this technology to cycling, and this is where the F1 technology meets cycling nowadays. I'll give you some insights into aerodynamics, why it's so important, where it's important, a bit of an analysis of the bike rider system, so that you can understand where you can improve the most through aerodynamics, how to make yourself faster, and then some tips for you, the rider. How do you improve your aerodynamics? And then as the next point, how do you improve your equipment? What should you be looking for on the equipment? And right at the end, we do a lot of work with triathletes, and we've contributed quite a lot to Patrick Lange. He's the Ironman world champion and world record holder, who was the first man to go under 8 hours in the World Championship last year in Hawaii, in Kona, and we did quite a lot of work towards that goal. So I'll present a few insights into what we did there with him. And of course, at the end, we can have a big discussion about whatever questions you might have to this presentation or to your own personal experience in cycling. So very briefly about me, Alexei already mentioned at the beginning, I'm the CEO and co-founder of Swisside. I have a Formula One background. I spent 14 years in Formula One as an aerodynamicist and a design engineer. At the end of my career in Formula One, I was the head of the complete Formula One car concept department, so designing the actual car. I used to be a racing driver in motorsport, which is actually how I got to cycling, because you needed to be fit to maintain lap times, especially over long distance races. And then I found my passion for cycling through motorsport. Love triathlon. I do a lot of triathlon, cycling in the winter, cross-country skiing. Meditation is a big part of my life. And my drive? Well, my drive is this bridge of this technology that's hooked up in this closed world of Formula One to bring it to cycling for the future of light mobility vehicles. That's a bit of another story, but basically my vision is in the future, in crowded cities, we're going to need better mobility systems, and those vehicles are going to be more like bicycles than they are going to be like automobiles. So I see that the automobile industry and the cycling industry are going to come a lot closer together. And that's one of the drives behind bringing this technology to cycling, and in the end to bring it back to mobility. That's another story. Today we're going to talk about aerodynamics of cycling. So basically, as I mentioned, my company Swisside is a spin-off from Formula One. We've managed to poach quite a few of the employees from my former team at Sauber, including the chief aerodynamicist who was there for 19 years, who's now a key part of our team. Together we've got over 60 years of experience in Formula One. And we're very much a one-stop shop for performance. That's a quote from the Team Sky, or now Team Ineos, technical head. Basically, if someone comes to us and they say, we want you to design a bike, we can do the whole thing, from the concept to the design, to the testing, to the production. So we can really cover all the bases, and we'll show you a few examples of that moving on. As I mentioned before, we're bringing these methods and technologies from Formula One, which currently don't exist. It's this closed world. We're bringing those across to cycling because they're really relevant for the development of the futures, the equipment of tomorrow. We take a complete system approach to what we're doing. So we also build our own wheels. We have our own wheel brand at Swisside. And when we started building wheels, we didn't say, or how do we build the fastest wheels in the world? We took a step back and we said, okay, what does the complete bike and rider system look like? And how do we make that complete system faster? And what do we need from the wheels to make that system faster? And that's the approach we take, which is very much the Formula One approach. You don't, in the end of the day, the only thing that matters in motor racing is the lap time. It doesn't matter if you've got the best aerodynamics or the most powerful engine or the best mechanical grip. It's lap time, and it's the same in cycling. So we try and apply this real world performance, this complete system approach. And the final thing, which I'll mention again later on, is my final point, is that we're a very data-driven brand. There's a lot of marketing hype in the cycling industry, a lot of people telling you what's good and what's not. Basically, it's very, very simple. Real performance can be quantified. So if it's faster, you can measure it, and that's what we're all about. So we'll move on from there. As I mentioned, we design wheels. So if you want some wheels, by all means go and check out our website. But a large part of what we do at Swisside is our aerodynamics consulting business. We actually, which we call Aerodynamics by Swisside, we actually design bikes and products for many brands. We help DT Swiss, who's actually our production partner on the wheel side. We help design all their aero wheels. We've designed numerous bikes on the market, including this Cube Aerium, which is currently aerodynamically the fastest bike in the world, which we designed in collaboration with Cube for one of our co-sponsored athletes, Andreas and Michael Raylett. We do a lot of work with Canyon, also together with many co-sponsored athletes such as Patrick Lange, the world champion. We work with Team Ineos, formerly Team Sky. We are their aerodynamics partner. We also do all of their performance simulation to help them determine their race strategy stage by stage. And we have a big pro athlete team. So both world champions, Daniela Ryf, 4 times Ironman world champion, and Patrick Lange, 2 times world champ, both of whom, since they've been working with us, have broken the world record 2 years in a row. Small contribution on the aerodynamic side from us. Daniela Ryf is also a co-sponsored athlete together with our wheel partner, DT Swiss. And we have many athletes in the top level pro scene, as well as many ambassador athletes. And all of these athletes come with us in the wind tunnel, and that's great because they benefit from our know-how, but we also learn from them. So we've had over 100 athletes in the wind tunnel in the last few years to learn, and which is some of the tips I'm going to try and give to all you guys today. So first of all, let's look at some of the aero technology. Now, I talked about the Cube bike, which we developed for in collaboration with Cube, and actually this was a project with Andreas Raelert, who's the rider we see here. Now, this isn't just a nice, pretty marketing-looking image. This is a real CFD simulation that took over a week to run on 250 cores. And what we see here is basically the turbulent air. This is basically, say, the maximum loss, pressure loss in the flow, and this is a visualization effectively of the drag that you see on the bike. What we use at Swisside is a really complete approach, and we call this our four-arm development process. On the left, we have, say, our understanding arms, which is performance simulation, where we can calculate the time on any given course with all of the parameter inputs. And our instrumented bike, our on-road measurements, using devices like this one here, where we can measure the aerodynamic drag actually out on the road. And then on the right-hand side, we have our core development process, which is CFD, computational fluid dynamics, basically aerodynamics in a computer, as well as our wind tunnel testing, which is really the cornerstone of what we do. So I'll take you through each of these 4 points. The great bit is all of the know-how that we have from Formula One is applicable one-to-one in cycling. It's very, very much the same approach, the same technologies, the same methods that we use. So here, for example, we can see on this particular slide, everything that's in blue and darker colours is where the maximum losses are in terms of aerodynamic drag. So CFD not only allows us to quantify in terms of the forces, simulated forces, we can also visualise the flow to better understand what's happening. So CFD is is the key development tool that we use. Here's a really cool simulation. Actually, this finished on Friday. This is an echelon simulation of road cyclists in an angle with a strong crosswind. This is a simulation we've done for Team Ineos in preparation for the Tour de France. And what you see is the maximum pressure loss, where the maximum drag is the chunks in red, and the next level of drag is the chunks in grey here. And we can see in this pressure slice why these sort of echelon formations form, because you can see how much disturbance there is in the airflow and how much the riders towards the back of the peloton or towards the back of the group are benefiting from this drafting effect. But we'll go into a little bit more detail of that later, but this is just to show you a little bit of the technology, what we get out of CFD and our simulation work. The wind tunnels are a really core part of what we do. The way we test a Formula One car is identical as the way we test in the tunnel with a rider. Very important that we can test accurately and repeatably. So again, sort of the methods we use for accurate, repeatable testing in Formula One, we apply straight away to cycling. Here's one of our athletes, Laura Phillip, in the wind tunnel with us just a few weeks ago. And we can also see one of our pressure measurement rake systems behind, which I'll show you later as well. It's a new technology, again, something we're just copy-pasting from Formula One to cycling. This is last week in the wind tunnel with Team Ineos. We did some testing with them in the UK, and we don't just test bikes and riders. We do a lot of development in suits. We do helmet development as well. We have various dummies and tools that we use for that sort of development. We recently designed a new helmet for Rudy Project, here's a sort of an example of the types of things that we use. We can also heat the head of this dummy so that we can also measure cooling. Obviously, when you put the helmet on, cooling's an important factor as well, so we're taking that into account with the design of helmets that we do. The next step is the sort of instrumented bike on-road measurements. Some of you may have seen recently we brought these new pressure rakes to the industry, where we're measuring the pressure loss behind the rider. Basically, the disturbance in the air can be measured in a loss of the pressure, the total pressure behind the rider. And we can quantify this with these sorts of rakes, which gives us a really important correlation between real world, wind tunnel, and also CFD approach. And again, actually it's nothing new what we're doing here. It's something we're just bringing from our experience in Formula One. Here you can see a picture of a Ferrari running around with a funny aluminium frame on, doing exactly the same thing, measuring the pressure loss behind the front wheels. And just as a quick side note to Formula One cars, basically a whole Formula One car is a front wheel aerodynamic management device. The front wheels create such a mess to the whole car that most of the car is designed around managing that loss. So that's why these sorts of measurements at the front end of the car in Formula One are quite important. We apply the same thing to cycling. And as I mentioned before, here on the front of the bikes we have these new special devices which we've been developing for a number of years. On the right-hand side, we have our instrumented bike, which we started in 2013 as a development project to understand this complete bike and rider system. This bike is covered in sensors. It has position sensors. It has aerodynamic sensors. We measure the height of the rider's body, and this was designed so that we could learn what does the rider need from wheels in particular, but also from the whole bike and rider system to be faster. And we've basically taken all of our knowledge from this bike and all the testing we've done with it over the last 5 years and condensed it into this device, which is a new device we're looking to bring to the market in the coming years, which is what we basically call our wind tunnel for the road. And we've already been using this device with Team Ineos in terms of the road testing we've been doing with them. So the idea there is not everyone can go into the wind tunnel, so we want to take the wind tunnel to the end consumer. But yeah, this is again part of the measurement technology we're doing for measuring on the road. The final step I mentioned is performance simulation. Basically, it's a glorified computer program where we input all of the parameters. So they can be environmental parameters like, where the wind, the course parameters, of course, what the course is like, how hilly, what's the height profile, the aerodynamics, the weight, of course, but then also the physiology of the rider. What's their power output? How much overpower can they bring for how many seconds? And this is a really important tool that we call our virtual pit wall that we've developed in particular for Team Ineos that we use for doing their stage-by-stage strategy optimization. And the great thing about this tool is we can calculate extremely accurately the time over any course. And more importantly, you can then go in and play with the parameters and see which parameters have the biggest impact on making the rider faster. And from this, we see exactly which part of the aerodynamics is important. Moreover, that aerodynamics is a lot more important than weight, for example, and it allows us just to find the optimum setup. So by combining all of these four development arms together, we have a very good picture as to how we go and optimize the bike and rider system to make it faster. So based on all of that, some key inputs or key insights into aerodynamics. I saw a question on the Dory come through, as of which speed is aerodynamics important? Basically, from 15 kilometers per hour, aerodynamic drag is the biggest resistance that you have. So even if you're riding down to the supermarket to pick up some groceries, actually the majority of the power you're putting into the pedals is to overcome aerodynamic drag. So it's very much important also for low-speed riding. Another thing is that aerodynamics is more important for slower riders than it is for pro athletes. Everyone has this impression in their minds that it's all about pro sport, it's all about super fast. Actually not. The reason for this is, when we make performance improvements and reduce the aerodynamic drag by, for instance, 5-10%, an amateur cyclist, a lower cyclist, is on the road for longer. They're on the course for longer. So the percentage time gain in absolute terms is actually greater. The other reason is we have this thing called sailing effect. New aero road bikes actually harness the wind, just like a sailing boat does, to help push it forwards. The slower you go, the larger the effective crosswind angle, and the more sailing effect you get. So it's a bit of a compound effect, but the end result is the slower riders, the amateur riders, actually benefit more from aerodynamic improvements than the pros. The athlete's body is 75% of the total aerodynamic drag. So even if at Swiss Side we build and sell wheels, I'm not going to stand here and say to you your first point of call is to buy our wheels. It's not true. Your first point of call is to look at your aerodynamics and how you can improve your position, the equipment you have on your body. So that's a very simple point, but one that can bring you a lot of time savings. The wheels do, however, have a very large impact on the aerodynamic drag of the rider. Now, you might think, how can that be? Now, I showed you a slide before of our instrumented bike. And what we saw is that the front wheel stability is really important for keeping the rider in an aerodynamic position for the longest period of time. So if, particularly in triathlon or time trial, we have these aero bars. Actually, I have a set here where we're trying to hold an aero position. If the front wheel is not stable aerodynamically and doesn't react predictably in gusty side winds, the rider simply can't remain in this aero position constantly, or they come off the power. They reduce their power output, both of which are a huge penalty for the overall speed of the bike. So what we discovered with our research is that the front wheel stability in particular is really important for keeping the rider in their aero position as long as possible, and thereby it has quite a large impact on the overall performance and the aerodynamics. So the wheels do have a big influence actually on the aerodynamics of the rider. With a good aero setup, you can save more than 10 minutes per 100 kilometres on the bike. So we're not talking about marginal gains, we're not talking about a few seconds here, we're talking about minutes and tens of minutes potentially over a longer ride. So there's a lot in this if you're a sporty rider, or if it's not just about time saving, it's also about saving energy. So it's an efficiency game as well. And I mentioned earlier, in triathlon, weight is actually relatively unimportant. And in road cycling, it's actually only important when you're riding up a hill and in an uphill time trial. So what we see is that for an average cyclist, you have to have an average gradient of 4.5% before weight becomes more important than aerodynamics. And that's over the entire course. And that's basically only an uphill time trial. For a pro rider, since they are faster and the aerodynamic drag becomes more important, that gradient's actually 7.5%. Yeah, and a perfect example of this is back in 2015, before we designed the Cube bike that I showed you before, we designed another version of the predecessor of that bike for Andreas Raelert. And we discovered that his original bike was aerodynamically pretty terrible. And he was losing 7-8 minutes on the Hawaiian Ironman World Championship course. So we went into the wind tunnel and we optimized that bike by producing some 3D printed packers, to change all of the tube profiles to get more out of the sailing effect, which I'll show you later. And we managed to improve the bike to the tune of around about 20 watts, which for him was around about 6 or 7 minutes of performance on the Kona bike course. Now, we added 1 kilo of weight to the bike in order to do that, because we didn't have time to produce a new bike. So we glued all of these profiles to them, painted them black, made it look like it was an original bike. The cost of that extra kilo of weight on the bike was 20 seconds. So 7 minutes of gains from aerodynamics, 20-second penalty versus the weight that we added to the bike. So it gives you a bit of a feel in triathlon of the level of importance of these things. But enough about that. A little bit of an analysis of the bike rider system. So we already mentioned before that 75% of the drag is the rider. The frame and fork and the wheels are each only 8% each. And 10% is the rest. Now, what is the rest? The rest is basically the drivetrain, the brake discs, and just for your interest, one of the most offending parts on the bicycle, if you use an electronic shifter, is a Shimano Di2 shifter. It's actually worth about 1.5 watts of power. So one of the trends we're seeing at the moment is these single chainring systems, so 1x11, 1x12 systems, and they're really great. I actually did 2 weeks ago a test with an athlete in the wind tunnel where we built from a 2x11 to a 1x12 system, step by step, removing all the parts, removing the derailleur, removing the hanger, and I think we totaled up at about 3 watts in the end, which is actually quite a lot in terms of, when you're looking to improve a bike by 3 watts, that's quite a bit. So anyway, that's a little insight to the rest. But in terms of the sailing effect distribution, I keep talking about this sailing effect, so I'll show you what that is in the next slide. But 65% of the sailing effect comes from the wheels. And so that's why the wheels are really important. And you can reduce your aerodynamic drag massively using this sailing effect. So for minimum aerodynamic drag, as I mentioned before, you need to concentrate on you, the athlete, the rider. But for maximizing the sailing effect, you need very good aero wheels. And as I mentioned before, stable and predictable aero wheels, because if you can't stay in your aero position, it's a waste of time. So what do we measure? whether it be in CFD or in the wind tunnel, first thing we do is we measure forces. So the main one we talk about all the time is drag, aerodynamic drag, quite simple. But we also measure a number of other things. We measure side force, so how much side force is there on the rider. If you've ever had a truck driving past you, you find yourself on the other side of the road, that's side force that you're experiencing that moment, so it also can't be neglected. One thing that we measure is this steering moment. So when side wind gusts, how much is the wheel trying to turn in your hands? And that's again what we discovered from our instrumented bike development, is how important this steering sensitivity is of the front wheel. And so we developed a special load cell and a special balance for our wind tunnel where we can actually measure that. And we were the first in the world to be able to quantify this steering moment, to be able to develop our wheels in a better way. Quite simply because we saw the impact it can have on the complete system aerodynamic drag. And then the final thing we look at is the stall behaviour. An aero frame or the aero wheels are like a profile of a wing, and they produce lift, and this lift is what produces the thrust or the drag reduction and this sailing effect. And like a wing, as of a certain angle of attack, the flow can no longer stay attached. It stalls, it rips off the profile, and then this lift or this aerodynamic benefit is lost. But what we need to make sure is when this happens, it happens in a very stable and predictable way, and there's not a sudden change in the forces. So we're also looking at this stall behaviour of our wheels and of bike frames, the products that we develop. Now, finally, what is the sailing effect? This is what a graph looks like, whether it's in the wind tunnel or out of CFD. And what we can see here is we start with a base drag level. So here on the vertical axis, we have the aerodynamic drag measured in watts of power. And on the horizontal axis, we have the effective onset flow angle, which we call the yaw angle. And as the yaw angle increases, you can see the power decreasing of the wheel. And actually, as around about 12 degrees of yaw angle, this wheel has zero drag. And further yaw angles after that is actually producing thrust. So you read sometimes in the press this talk about negative drag. And actually the front wheel on the bike is the only part of the bike that actually produces this thrust, but this drag reduction happens everywhere on the bike where you have a good functioning aero profile. And you can see how important this is. So in a course like Kona, so the zero, to put this in context, 20 degrees of yaw, the effective onset flow angle, this range is what you see when you're riding a bike. About 95% of the time you will see something between 0 and 20 degrees. You see more 0 degrees than you do 20, but this is the range which we see in the real world. In a course, a really windy course like the Ironman World Championships in Kona in Hawaii, the athletes are riding with an average of around about 15 degrees of crosswind, or 15 degrees of onset flow angle. And you can see on the front wheel alone at 15 degrees, the wheel's producing around about -6 watts of drag compared to almost 15 watts that was producing at the beginning. So that's 20 watt drag reduction to show you how potent this sailing effect is and why the riders need to use this aero equipment. What happens if you go to shallower section wheels? Quite simply, you get less sailing effect, but you also get less sensitivity in the front wheel because you've got a smaller sail. So at some point, the big deep section wheels like this 80mm wheel I showed you before, it becomes unrideable in a stormy condition, so you need to ride a smaller wheel. So this just shows you the different level of sailing effect, the different level of aerodynamic performance that you get from each of these wheel depths. So that's the type of things that we measure in the wind tunnel, but we also measure, I mentioned before, the pressure loss. So we have this here is world champion Patrick Langer in the wind tunnel with us this is a picture from 3 weeks ago. And we have this rake, which is a 1 metre wide system with a whole lot of pressure measurement probes on it. And we scan up and down behind the rider during a run at various yaw angles, the various crosswind angles. And we can quantify and visualise how much pressure loss there is, which is actually the aerodynamic drag. And that looks like this. So we create these sorts of plots where we can really see the pressure loss. And for example, here in this contour plot, everything that's red is 100% energy in the flow, and everything that's dark blue is 100% total loss of energy in the flow. That means the wind is actually being pulled along with him. And like this, one of the problems of testing in the wind tunnel is you get a result. We change something, you get a result, but you can't really pinpoint exactly what the mechanisms were that led to that change. But with this sort of pressure measurement technology, you can really understand, the helmet loss got smaller or the shoulder loss got narrower. So you can really start to understand what is affecting what, and it helps us to be able to optimize in a better way. So again, some of the technology that we're bringing, again, straight from Formula One to the cycling industry. In CFD, you've got all sorts of different pressure, all sorts of different visualization possibilities. Here we've got streamlines combined with pressure loss, so you can see both the flow angularity. This is a section through this road cyclist. So you can really, again, understand in CFD what mechanisms are at play. We had, again, on the Dory a lot of questions about drafting, so I thought I might include a slide on drafting. Here is a simulation we did on drafting in triathlon. So in triathlon, there's a 10-metre rule. You're not supposed to be more than 10 metres closer to the rider in front. And all of the pros and anyone who's had a bit of experience will notice that even at 10 metres, you're still not putting as much power as you do when you're out on your own. And the truth is, even at 10 metres, there is a significant drafting effect. And you can see this in this image here. This image is a plot of velocity in the flow, where we have, full speed velocity is red, and everything down to almost 0, 2 metres a second is here in blue. And you can see at 5 metres, well, the airflow is significantly slower, hitting the rider in front, and even at 10 metres you can see there's still quite a significant drafting effect just visually from these images. And how much is it? Well, one of the questions in the Dory was if I'm 20 centimetres or 50 centimetres from the rider in front, what's my drag saving? Well, my drag saving's around 40% in a time trial position. If you're in a road cycling position, it's actually even higher. It's 45, almost 50%. And if you're riding, for example, in a peloton, where the speeds are often, say, around 45 kilometres an hour, 50 kilometres an hour, at 45 kilometres an hour, that's a 90 watt drag saving. So it's quite significant. And before you get angry the next time you're riding around and some guy has hooked in on the back of you and getting a free ride, and you think, this guy's getting drafting, actually that guy behind you is reducing your drag by around 4.5%. Because he's carrying some of your drag from you. So actually both of you are faster. So don't complain when the guy's getting a free ride anymore. Even at 5 metres in a theoretical world, there's still a small gain, but in the truth there's not really much. But anyway, coming back to the 10 metres, even at 10 metres there's still around about a 13% drag reduction for the guy behind. And this correlates really well with measurements we make with these sorts of devices out on the road, and also just from the pro athletes. They know that when they're in the pack, they're pedaling 20, 25 watts less than when they're on their own. And that's why these big trains of triathletes build in these big races, because there's quite clearly a big balance, a big advantage to be had. So a little bit of an insight into drafting. But now what it's all about, how do you make yourself faster? And where's the potential? So here's a picture of me in the wind tunnel having a bit of a play. You've got to have a little bit of fun when you spend so much time in the wind tunnel. I wanted to know what the Superman position was like, and this has got actually the lowest drag number we've ever measured in the wind tunnel if it means anything to anyone, a CDA of 0.132. But of course, without being able to actually pedal on the pedals, it's not really going to bring me much. But anyway, a little bit of fun. So, a more serious example. I did a test in the wind tunnel. When I first came to cycling, or came to triathlon, I'm like most amateur athletes. I came with a road bike. I put some clip-on aero bars on the front of it. I had a normal, I had a standard road bike with cables exposed, all of these sorts of things. I already had aero wheels, of course, because I was a fan. They look good too. It's not an unaerodynamic setup. I already had a one-piece suit, albeit without arms. But anyway, then a few years later, I created a company. We designed some bikes, we designed some wheels, and I managed to take one of those bikes and those wheels into the wind tunnel, as well some suits and a proper time trial helmet. And the question is, how many watts did I save? How much percentage drag did I save? So we can break it down. We did the step by step, and basically, let's go to the headline number first. I saved 38 watts of drag at 35 kilometres an hour. So I've got the numbers in red are at 45 kilometres an hour, and the numbers in blue are 35. For this presentation, I'll quote numbers at 35 kilometres an hour because I think that's more It's more speed that I ride, and I think it's more a speed that most of us ride. But it's over 30% drag saving moving from those setups. And if we break it down, we can see the bike alone brought 22 of those 38 watts. The TT helmet brought 6 watts. The suit, reminding you I already had a one-piece suit, but I went just to a better fitting suit, was another 4 watts. I went to a narrower arm position. We see this brings quite a lot. It's not very comfortable to ride, especially if you want to try and ride a full Ironman. But you see a lot of the pros riding this, so I tested it, and for me it did bring another 4 watts. And the big one, shaved legs. This was on the Dory. Now, this was a pretty significant gain. 4 watts is a lot for shaved legs at 35. I specifically let my legs grow really hairy over the whole winter for this test, right? And between 2 runs, I got out my Phillips, whatever, man shaver, and I ground it all off without touching my suit. I left my helmet on because we don't like to touch anything between 2 runs, and we got 4 watts. So it was really a significant gain, and it was real as well. So again, on a time trial bike, we can see massive savings, but a lot of us ride road. So let's do exactly the same test and on a road bike. And here we got one of the editors of one of Germany's biggest cycling magazines, Moritz Pfeiffer from Road Bike magazine, and we did the same thing. So we asked him to bring material of his choice, 2 bikes. He brought a standard road bike. It already had actually some slightly deep section wheels, I think about 35 millimeters deep, and then he brought a full aero setup with a full aero helmet, one-piece suit, proper aero wheels and aero bike, and we did the same old test. And how many watts did he save? So I think in the last slide we were at about 30% and about 38 watts. And this one we're also at 37 watts. The drag is higher on a road bike, so the percentage is low, but still 20% saving we made here. And again, the difference just between the road frames was 11 watts. The difference between the lower bar position, we'll come to this in a minute. So the difference between being on the top bar position, on the brake hoods we call them, to going on the lower bar position was 8 watts in itself, and I'll show you actually a breakdown of those positions in a moment. One-piece aero suit, 7 watts. The air doesn't like skin. So first thing I'll show you later, having long sleeves, or the longest possible sleeves that are allowed within the rules, is actually always a benefit. And having a one-piece suit means you have the minimum number of wrinkles and folds and the best fit. And that's all measurable in the wind tunnel. And like we say, focusing on the rider, on you, the athlete on the bike, which is 75% of the drag, that's why we always see big gains from the apparel. The aero wheels, in this case, like I mentioned, he already had semi-aero wheels, so we only had a 4 watt gain. That can be easily double when you compare to a set of standard aluminium wheels, which are maybe 25, 28 millimeters deep. Aero helmet, going from a standard road helmet to an aero road helmet. There are these new sort of aero road helmets. We've done a lot of helmet measurements in recent times, and they really do bring something. 3.5 watts there, and I threw in my shaved legs number on top of that just to add it. So yeah, big savings available there on the road bike as well. But a lot of us probably don't speak speak about watts. So in the end, what matters is time. So let's look about what this means. Let's translate it to time. So what I did with our virtual pit wall, with our performance simulation software, we ran a sim, and we took a 100 kilometer course with 1,500 height meters of climbing, so that's a pretty hilly course, a 75 kilo rider with an 8 kilo bike and a power output of 200 watts. Now this is quite typical of a normal sporty athlete that does a bit of training. It's sort of pretty much what I'd be doing. And we ran this sim to see what the time benefits were. And basically here's exactly the same thing we see again. Over that 100 kilometers with 1,500 meters of climbing, we see over 10 minutes of time saved for that particular athlete. And again, over 3 minutes for the road frame, 2 minutes for the lower bar position, the suit, 2 minutes. You see all of these minutes adding up. It all makes a big difference. And a lot of this stuff doesn't cost. So obviously if you want to go and upgrade your bike, that costs a lot of money. But certain things like going out and buying a one-piece suit, going out and buying an aero helmet, working on your position, that doesn't cost you anything. So there are a lot of gains, a lot of aero improvements here you can make without spending a lot of money. So, some tips on the rider position. I mentioned the upper bar positions before. Now, basically, go lower. Now, there's a disclaimer I'm going to say here. It's a discussion I have a lot with bike fitters. Of course, if you get yourself into a really completely contorted position where you can't push the pedals anymore, you might save 50 watts of drag, but if you lose 70 watts of power to the pedals, you're obviously not winning. So make sure it's a position that you can hold and you can ride, but this gives you an idea of where the gains can be made. So if we take the reference of being on the brake hoods on top of the bar, and then quite simply in this case, moving with straight arms down to the lower drops. That's the same test we did before with Moritz. We see an 8 watt drag saving, and that's 2.5 minutes per 100 kilometres around about. Now the next fastest position again is actually back up to the top bars and bending the arms. So 90-degree bent arms sitting on the top bars. And actually this is quite a comfortable position. I can actually ride this for most of a ride. And you can see that brings a 5.5 minute saving per 100 kilometres. And all that requires is a little bit of core strength and a little bit of stretching. Now, if you want to go to the real extreme, like our sprinter friend here, lower bar position, bent arms, and you're saving 30 watts at 35 kilometres an hour. Now, this guy, he's doing something like 60 or 65 kilometres an hour, and those 30 watts are more like 100 watts at that speed. So you can see how important the aerodynamic drag is, in particular in a sprint situation. So it gives you a little bit of a sensitivity study of how rider position affects the aerodynamic drag. Yoga. If you want to ride these positions, especially if you're triathlete, especially if you want to do a long distance, if you're really crazy and you want to do an Ironman, you're on the bike for 180 kilometres for 5 hours, maybe more, you want to do some yoga. They've got some great yoga classes here at Google, I hear, so great. Sign up. It's one of the best things you can do for your aerodynamics. Strengthen your lower back, stretch out your lower back, core strength, flexibility. Right. Now some aero tips for your rider equipment. So I mentioned before, suits. Then the air doesn't like skin. So in triathlon, we're not allowed to have full length arm suits, but actually the biggest gain to be had is down to the elbow. The extra addition of covering the forearms actually doesn't bring all that much because they're not so exposed to the wind because they're quite horizontal. But this part is really important. So try and avoid suits without sleeves. A suit with sleeves is always significantly, measurably better. If you're road cycling, a one-piece suit for race day will bring you a lot. So consider a one-piece suit for race day. In triathlon, and most people are riding a one-piece suit nowadays anyway. The suit must fit as tightly as possible with the minimum number of wrinkles. It's really hard. You can't generalize and say, this is the fastest suit in the world. The reason for this is there's a big interaction with the rider's body shape and their position, their head position and so on. So we see with some riders one suit's better, with other riders another suit is better. But what we can say and what we do see in the wind tunnel with our testing is that a suit that fits tightly with the least number of wrinkles always is better than one that's a bit loose. If it's wrinkly and loose on the front where it sort of crumples up here like this, that doesn't make much of a difference actually, because here the wind is like a stagnation zone, the wind almost comes to zero, but it's where the wind is really high speed, around the sides, around the outside of the arms is very important, and sort of around the sides of the legs. So these are the really important areas to look at. So if you're going to the shop to choose a suit, that's the best recommendation I can give you. And for the guys, a lot of people like to have an opening at the front, particularly in triathlon or cycling, to be able to go to the bathroom. Like I said, the front end of the suit's actually relatively unimportant. So these suits that have a partial opening in the front, they're not a disadvantage. How much potential is there? There's a good 9 watts at 35 kilometres an hour between a two-piece apparel and a good fitting triathlon suit. If we take a look at helmets, aero helmets do make a difference. I've spent the whole winter testing and optimising helmets. You saw before our helmet dummy. We do tests with athletes. We do tests with the dummy in different head positions, different body positions. Got a really good idea of what's working and what's not on helmets. There's a few tips I can give you. First of all, aero helmets are a really good investment. They don't cost a huge amount and they do bring a significant performance gain. Don't forget the cooling. There are a lot of helmets out there on the market that basically have no cooling. Now, if you've ever seen the pictures of the Hawaiian Ironman when they're riding out in the lava fields, I tell you what, if you don't have cooling there, you overheat the processor, you're not going to be able to have a strong race. And actually, we're doing quite a bit of studies at the moment in the correlation between cooling, in particular cooling of the head, to the power that you can bring to the pedals, because we believe there's a strong correlation. So don't forget the cooling. And a really good tip for that is, even as an aerodynamicist, when the helmets with visors came out, it's like, oh yeah, visors great, they're going to make the flow a lot cleaner. Actually, we see very little difference between visor and no visor when we measure in the wind tunnel. And we've done this test dozens and dozens and dozens of times. But what we do see is a significant shift in the cooling level. When you remove the visor, you increase the cooling by anywhere from 20 to 40%. So it's a really great cooling tip. So on a really hot day, you can choose to not run the visor and instead run sunglasses. Or on the contrary, on a really cold day, put the visor on and you get a little bit more heat to keep your head warm. Short tail helmets, again, the whole marketing story. We read so much marketing in the press that brands are bringing out these really short helmets and they're really great and they work really well. Well, they don't. I'm yet to measure a really short tail helmet that really works. A little bit of a tail always helps. And so, they don't have to be like the helmets we had 15 years ago with like all go all the way down to the small of your back. It doesn't need to be that long, but a certain length of helmet like we see on some of the lower two helmets here really does make a difference. And that's the typical difference you see on the right-hand side between the new range of aero road helmets compared to sort of standard helmets. This is a helmet from the brand Scott. A Scott Cadence it's called. You'll see it's slightly longer. It's got closable vents to reduce the cooling level. This really does make a difference. So there are some tips on helmets. How much potential is there? For a standard road helmet to an aero road helmet, there's around 4 watts at 35 kilometers an hour. And then going up to a full time trial helmet, there's another 4 watts again. So it steps of 4 watts each time. So plenty of potential there. Frames, bikes, wheels. Every brand claims that they've got the quickest product, including Swisside. But trust the brands to deliver proof. I mean, if it's faster, I said at the very beginning of this presentation, if it's faster, it's measurable. Not just in a wind tunnel, you will measure it on your tacho. If you've got a power meter, you can see it in the power. If you don't have a power meter, you can drive the same circuit twice and the same course twice, and you'll see that you're faster. So trust brands who deliver real data with benchmark comparisons, and look for independent test results. There's a lot of aero-looking stuff out there, which is very, very not aero. So really be careful, especially if you're making the big investment on a bike frame. Some of these bike frames are 10,000 euros plus nowadays. Look for the independent test results. How much potential is there? Well, there's at 35 kilometers an hour. There's around 18 watts in the difference between a good frame and a bad frame, whether that's in a road or a T-bike. It can be even bigger. I've seen some pretty disastrous bikes out there. Integrated cables are very good, but we'll get into that in a moment. And the wheels, again, the difference between standard wheels and good aero wheels, around about 7 watts. But like we saw before, the sailing effect can be much, much, much higher than that. So you can double that number if you're looking at a windy course. Bike equipment. Cockpits and bottles. So we get a lot of questions about where should I put my drink bottles. Now in UCI road racing, you're only allowed to put the drink bottles within the triangle of the frame. A round bottle is really bad. So round bottles are quite terrible. So if you're not UCI racing, if you're doing triathlon, do whatever you can to not put a round bottle on the frame. If you want to put a bottle here, you can put an aero bottle. There's a bottle from the plenty of aero bottles out there at the moment, and they work very well. Coming to, the best place to put bottles is behind the rider, behind your butt. This is an area we saw in some of the CFD images. Lots of blue here, lots of total loss flow. Basically, you're pulling a pocket of air along with you. So the relative airspeed to your body behind your butt is 0. So it's really the best place where you can put bottles. So you're not allowed to do it in road racing, but in triathlon, you're absolutely allowed to do it. So it's a great place to put your bottles. Aero cockpit. makes a very big difference. So you see the new generation of aero bikes have an aero handlebar with a very flat-shaped, aero-shaped base bar. They really do make a difference. And integrating the cables alone are around about 3 watts of drag. So removing the cables and integrating them makes the bike a little bit of a pain to work on. But if you're looking for performance or to save energy, to be more efficient, an aero cockpit with integrated cables does bring a lot. And those two things bring up to around about 8 watts at 35 kilometres an hour, more or less an equal gain from each of those two things. Tyres. You're probably wondering why I'm talking about tyres and aerodynamics. But believe it or not, we've talked about the sailing effect. We talked about the front wheel, which is right in the front of the flow. The selection of tyre on the front wheel of your bike, road or triathlon or TT, has a huge effect. And it's absolutely the most important thing for the sailing effect. If you pick the wrong tyre, you will lose all the sailing effect. And it's really confusing. It's really confusing for the end consumer. Particularly Continental has a tyre called the Conti TT. And you think TT, time trial, this has to be the fastest aero tyre. It's a slick tyre, has no tread on it at all. Put that on the front of the bike, you'll destroy the aerodynamics of the front wheel. It's a bit of a complex phenomenon. You need a certain amount of sidewall tread on the shoulder of the tyre. This trips the flow from a laminar to a turbulent state. Without that trip, the flow won't stay attached, the wheel will stall, you lose your sailing effect. It's very difficult to say exactly which tyre works and which tyre doesn't by looking at it. I have no affiliation to Continental, but the Continental GP4000S2, which is their older tyre, actually is the best functioning aerodynamic tyre we've measured in the wind tunnel to date. It's also a really good tyre in terms of grip and rolling resistance and puncture resistance, so a very good choice. Their new 5000 tyre isn't quite as good as the 4000 aerodynamically, but it's got lower rolling resistance. It ends up being around about an equal game at the end, but some good tyres to be had there. The best tubeless tyres, tubeless is really good, it has a significant reduction in rolling resistance. Best tubeless tyre is the Schwalbe Pro 1 in terms of aerodynamics that we've seen, has pretty good rolling resistance as well. On the rear tyre, you don't have to worry about the aerodynamics. It's in the shadow, it's in the drafting effect of the whole rest of the bike, so you don't have to worry too much. But on the front tyre on your bike, really do look to pick a good aerodynamic functioning tyre. In this month's Triathlon magazine, if you happen to speak German, there's a huge tyre test that was done in the wind tunnel to show the aerodynamic performance of all the tyres combined with rolling resistance testing and so on. So a very good read. Lots of potential. Well, 3 watts, it's a bit of an understatement, to be honest. If you put the wrong tyre and you're riding in Kona, like we saw before, that's going to be more like 20 watts of a penalty. So there's at least double that when you're looking at aero tyre. So the last thing before I wrap up, I'll give you a real quick behind the scenes look into Project 101. So Project 101 was, we support Patrick Lange, the World Ironman champion, since a number of years now. And in 2017, he was 101 seconds away from the magic 8-hour mark. And we made it our goal as a team to try and get him underneath that 8-hour mark in the World Championship in Kona. And so this became known as Project 101. We pulled in a few partners to help us with this, including Sauber Engineering, my former Formula One team employer, with whom we still have very good contacts since we like to steal their staff, and Canyon, who's the manufacturer of and co-sponsor of Patrick. So basically what we saw from our CFD work and our wind tunnel testing is that the front end of the bike, particularly because he has quite a strong 15-degree arm angle, that the exposed tri-bar extensions were quite detrimental to his aerodynamics. So we said, okay, well, we're going to try and integrate these to make them part of his arm. So we scanned his arms up. We also scanned the pads. There's a great video on this, by the way, online that you can see at Swisside. And we designed a new cockpit, and I've got some of the parts here. So the first thing we did, we designed some parts and we went to the wind tunnel because, you know, before we go manufacturing a part like this in a road-ready state, which costs a lot of money, we want to make sure that it actually does something. So we took these parts to the wind tunnel and we got a really significant performance advantage. And actually, one of the even bigger performance advantages that Patrick fed back to us is the comfort, because he was no longer leaning on the bars with 2 points on his elbow pads and on the tips. He could rest along the entire length of the bar with his arms. That gave him a lot more comfort. He didn't have to grip the end anymore, and he could just quite relaxed lean on the bike. Gave him also a lot more control on the bike. So that was a really good step for him. Once we saw that it was good, we got in contact with our friends at Sauber, who'd recently invested in 3D metal printing technology. And because to produce parts like this in carbon fibre in such a short space in time, I mean, this picture in the wind tunnel was about 2 months before the Kona race. It was impossible. And also, we saw that we could probably make a lighter part using 3D printed technology, because you can put different level of reinforcements. You can have extremely thin wall thicknesses. So the parts we built were a combination of titanium and aluminium. They had wall thicknesses as low as 0.5 millimetre thick with internal webbings and reinforcements. And we actually managed to make these parts lighter than the original carbon bars, but also a lot more comfortable and a lot more aerodynamic. And together with Canyon, we did a lot of structural testing on the parts at Canyon to make sure, of course, the last thing we wanted to do was have these parts break halfway down the bike course. That would have been rather embarrassing. I don't think Patrick would have been too impressed. And on race day, look, in the end of the day, we deliver our bit, which is to make Patrick and our athletes as fast as possible. But he was able to deliver in terms of his performance on the day. And he not only went under 8 hours, he did the course in 7 hours and 52 minutes, 39 seconds, I believe. Okay, there were very good conditions on the day, which made it a fast day, but definitely the contribution did something. So that's a little bit of an insight into aerodynamics and cycling. I hope you've been able to take something out of it. And of course, now I'm open for whatever questions you can throw at me. I'll answer them the best I can.
I'll do the first one from Dori, then you guys can think meanwhile. So many people don't have a wind tunnel to optimize their position. How big is the typical gap between efficiency of a position before and after calibrating by an expert?
Yeah, so we see a good bike fitting. There's a lot of really simple bike fitting solutions nowadays. This is a green screen type of thing. So rule number one in aerodynamics is frontal area. Reducing frontal area reduces your aerodynamic drag. So you see by doing a good bike fitting, first of all, to ensure that you can bring the maximum power to the pedals, and then with this sort of green screen or frontal area analysis, we see significant performance improvement. So, around about 10, 15 watts is definitely possible with a simple bike fitting. Yeah.
Question from audience.
I'm a big expert, and I remember at some point the FIA started limiting the number of CPUs you can use for CFD computation.
Yep.
How big of a limit was that? How did you play around that? I don't think that exists in your current environment.
Yeah.
At least.
Yeah, so the great thing is we have no limits on what we can do with our CPU hours and whatever. It was a huge limit in Formula One, which was a huge disadvantage for certain teams like Sauber, who had invested a huge amount in their CFD technology. But what was really counterproductive about that was it just forced the teams to invest tens of millions in useless technology to get around the rule. So how do they calculate in a different way? What type of other meshing elements can they use? How can they solve in different ways to reduce the CPU hours? It's not relevant to improving performance in the world. So actually those sorts of things were one of the reasons I decided to leave Formula One, because there was a lot of irrelevant development from very smart minds going into developing stuff that had no use. So it was a big hindrance. But yeah, we can do whatever we want. Thanks.
Hi. Yeah, hi. Thanks for a super interesting talk. Can you weigh in on the tire and rim width debate? I feel like things are getting wider and wider.
Yeah, no, really, really good point. Does make a difference. So we're seeing the new generation of wheels coming out are slowly getting wider. Years ago, we had inner rim widths of 13 millimeters, 15 millimeters. The current aero wheels are 17, maybe even 19 millimeters wide, and we're seeing the trend to go even wider. Like I mentioned before, there's a kind of rule of thumb number one in aerodynamics is frontal area. So when you go to a wider rim, you increase the frontal area. But there's the frontal area drag, we call the parasitic drag, but then there's also the form drag, the profile drag. And what we do see is that you get less profile drag when you go wider, because the wider tire forms a more smooth shape with the rim, and we also see the potential to get a little bit more sailing effect. So the trend to go to slightly wider rims definitely brings something. To go really wide, like there's some rims out there that are like 22 or 23 millimeters wide, that's not necessary. Actually, the drag is higher because of that. So there's a sweet spot in there, which is around sort of 17 to 20 millimeters in my experience.
Hi, I asked a question in the doorway and I had to step back for a few minutes, so I'm not sure if you answered it. It was about things like rotational drag, and I picked up a discussion from a bit of a kerfuffle with somebody called Cambini, who've been doing some testing and found that some wheels perform really badly because of yaw angle variability and rotational drag. So I was just wondering if you'd had any thoughts on that. And I should mention, as full disclosure, I've got a pair of Flow 60s, which I'm actually very happy with, but did very poorly in this test.
Okay, so firstly, to answer the question on rotational drag, I'm not aware of the people you mentioned that were doing the rotational drag testing. As far as I'm aware, we've pioneered, together with our partner DT Swiss, the whole rotational drag question. So a number of years ago, we identified in CFD, because in CFD you see all of the forces. You can see the forces on the spokes individually, to the rim, the tyre, and we saw that the rotational drag was a significant proportion of the drag. Actually, it's between 20 to 30% of the actual drag that you get on the wheel. And actually, that's not measured in the wind tunnel, because in the wind tunnel we drive the wheel with some rollers, and the energy, the power that drives the wheel can't be measured repeatably. So we're actually not measuring the rotational drag in the wind tunnel. But we do measure the rotational drag separately. So we have a special rig which we developed as a collaboration project together with DT Swiss, where we put in the wind tunnel and we can measure the rotational drag forces really, really accurately. And actually our latest generation of wheels are optimized for this rotational drag. So in particular the spokes, and going to thinner spokes is a really important step. And it's one of the reasons why we see that multi-spoke wheels don't tend to work very well. So these 3-4-spoke wheels, there's many reasons why we're not a fan at all of those, which is why we haven't developed one, because they're not stable and predictable in crosswinds. It's one reason. Because the position of the spoke is constantly changing whenever there's a wind gust. So sometimes the wheel will turn one way, sometimes the wheel will turn to another way. So this is one of the reasons we see the 3-spoke wheels in particular to be no good. But the other reason is rotational drag. The profiles that they're using, the structural profiles, are actually quite inefficient and create a lot of drag, a lot more than you get from, for example, 16 bladed spokes. So yeah, rotational drag is a really important topic, and it's one that we do consider in the development of our products. And again, on our website, you can actually read quite a bit about rotational drag.
Okay, thank you.
There was another question from Steve. Legs, feet moving. Do you test iron pedaling?
Yes. So when we have the rider on the bike, we're always pedaling. Actually, the position of the legs is a huge difference. So if you test with static legs, horizontal legs, so it's a good tip for you. If you're descending on a downhill position, horizontal legs is about 30 watts less drag than vertical legs at 45 kilometers an hour. And because aero drag power increases with power of 3, yeah, it goes it goes a lot higher, a lot quickly if you're doing 60, 70, 80k an hour. But yeah, we always test with rotating legs, and we actually match, when we're doing yaw scans, we actually match the rate of feed of yaw angle to the cadence, so that we make sure we get complete revolutions with each pedal stroke for each angle of measurement for yaw.
How about dimples like zip uses on their wheels? Are they effective, and why are they not used on other pieces of equipment?
Quite simply, a fantastic marketing tool. Doesn't bring anything. The idea behind dimples is you want to trip this boundary layer from this laminar state to a turbulent state. But the fact is, I mentioned before, this has to happen on the tyre. Once you've tripped the flow to the turbulent state, you actually want the surface behind it to be as smooth as possible. You don't want to increase the amount of turbulence in the flow. Yeah, we've looked at various technologies. There's dimples is one way you can do it. You can do it with other sorts of turbulators on the surface. But we discovered you need turbulation on the tyre, but not on the rim. So great marketing. It sold lots of wheels for them, but aerodynamically, it doesn't bring you an advantage.
So does that apply to the sawtooth rim shape that I think Zip have got on their wheels now?
Yes, it does. We developed the sawtooth wheel actually in 2015. These things are known as tubercles. The leading edge of whales have tubercles on them to deal with strong yaw angles. Now there's strong yaw angles they see when they're changing the angle of their fin in the water. Now we played with tubercles on the leading edges of our wings in Formula One for many years, mainly on the rear wing flap, because in Formula One they introduced a thing called DRS, which is the drag reduction system. So they open the flap down the straight and they snap the flap closed when you jump on the brakes. We had a real problem with the flow reattaching onto the flap when it shuts again. So we added these tubercles to generate a bit of turbulence to try and help the reattachment of the flow. But we never got it to work, which is one of the reasons you've never seen tubercles on a Formula One car, because we were surely not the only ones playing with that. Now, the reason it works in a whale is in water, and the density of water is very different to the density of air. Now, you know, we thought of the fact, oh, hey, it would be really good to do a marketing feature, something that's visual aerodynamics. The biggest problem with aerodynamics is that you can't see it. So as a brand that's really advanced in aerodynamics, it's really hard to sort of show you that our products are really superior. So we thought, oh, let's try and get tubercles to work. Let's see if they can work on a wheel. They increased the drag by about 20%. What they did do was slightly reduce the steering moment, but actually with our latest designs we've been able to reduce the steering moment even more. So yeah, we've designed such wheels, and we see it as not really a relevant technology for cycling wheels, which is why we haven't pursued it.
I got the last question from Dory. On the Canyon Speedmax CF SLX, is it more aerodynamic to use 0, 1, or 2 Elite Chrono CX water bottles?
Right, okay. So the Speedmax CF SLX is the bike that Patrick Langer rides, and also the bike that Laura Philipp rides and Daniela Blamil, 3 of our athletes. So we know this bike very well. And yes, I can answer positively to this. I can answer that question because I've tested all sorts of bottles on these bikes. The Elite bottle is neutral on that bike, only on the down tube. You don't want to put one on the seat tube. So on the down tube it's quite neutral, and you want to mount it in the lower position. When it's mounted in the lower position, it's neutral. In the upper, there's 2 bottle mounts on that bike. The lower position is the best one, and the bottle is completely neutral there. Doesn't bring any performance benefit though.
You mentioned your work with Patrick Langer.
Yes.
Is the airbox the only thing you changed on the bike?
On the bike, it's the only thing we changed. On Patrick's body, we changed some other things. We're looking, each year we like to do a new special project, and I can tell you we're doing a new special project for Patrick this year. So keep your eyes peeled in Kona, and we'll see what we can get up with, if we can do it in time. Of course, with the blessing of Canyon, because we're not allowed to change anything on the bike without their permission, so we need them in the boat. So I'll be doing some political managing in a few weeks' time.
some pretty pictures of modelling an echelon going through wind. What actionable advice do you get out of that? We all know that echelons work because we see it. Are you able to tell them slightly different positions, slightly different improvements?
Yeah, so without giving too much away, because this is fresh development, fresh off the CPUs. Yeah, what we're looking is at what's the level of drag reduction, what are the different spacings, what's the optimal spacing, particularly in an echelon. You might have a 30 degree of crosswind, but it doesn't mean that the echelon needs to be at a 30 degree angle. So we're just trying to quantify and educate the team and the riders what's the most efficient positioning to have in the various wind conditions, and yeah, that's sort of along the roads that we're going. And also for our virtual pit wall, for the strategy tools that we have for them, which they can also use live during a stage. If the conditions are changing, they can enter new conditions and sort of see for themselves what's the best strategy. So it's important that we have the input data for that, and because it's really difficult to get all the riders out on the road to make these measurements, although we did a whole lot of measurements last week. There'll be a video coming about that leading up to the Tour de France that will be released by us and Ineos. But we do a lot of work in CFD because it's just it's very accurate when the way we do it, so we can get a lot of the data for this from CFD to input into this tool.
So a question about riders switching bikes mid-ride. It seems to be a bit of a trend now, and when they had the open stage of the Giro, where you had a very flat bit of the TT, and then it went a bit vertical, was the time they saved from switching to the larger road bike, was that worth the time that it took them to switch bikes?
Yeah, it's in the end, it's quite a simple calculation. So you know the aerodynamic drag and the power, say the energy consumption of that bike and rider system for a time trial bike, and you know the energy consumption of the system for the standard road bike on a really steep uphill course. And yeah, when it gets really steep, when you're talking about 15% plus, it's actually a no-brainer. You are quicker on the ultra lightweight road bike setup. So that's why, you know, I say aero is king. You're always fast on the aero road bike. There are exceptions. For example, in a big Grand Tour race where the whole peloton rides to the bottom of a climb, and it's a climb finish. It's a finish at the top of the mountain. So basically, it's an uphill time trial. So there are cases when the amount of time required to switch the bike, that costs you time, costs you 10 seconds, say, for argument's sake. You've got to make sure that the time saved going up the climb on the lighter weight setup saves you more than 10 seconds. You know, if it saves you 20 seconds, you definitely do it, because it doesn't have to be just about time. It's also about saving energy. So the rider can really have a strong sprint at the end, for example, to win. So again, it's an energy game as much as it is a time game. So yes, there are cases where switching bikes does actually make sense during a stage.
With this, we're gonna wrap up. Thank you very much for coming.
Hugely appreciate it. Extremely useful.
Thank you. Thank you, everyone. Thank you.